Hello to everyone, and thank you for joining us for the latest installment of the SDNS webinar series. I'm Elise Roberts, and it's my pleasure to welcome you to today's session, organized by the section on statistics in defense and national security. I'm thrilled to have Cole Molloy with us today. Cole is a data scientist at the Johns Hopkins University Applied Physics Lab. He bridges cutting-edge machine learning and natural language processing with real-world applications in scientific and engineering challenges. His work includes everything from data handling and report automation to developing interactive visualization tools, all while pursuing his Ph.D. in computer science at Johns Hopkins University. His research focuses on how NLP models encode social behaviors and how we can use that knowledge to better understand human written texts. Today, Cole will be presenting SysChat, a retrieval augmented generation tool that combines information retrieval and large language models to answer user questions about mechanical systems. In his talk, he will discuss enhancements to LLMs to improve reasoning capabilities, walk us through SysChat's architecture, and explore classical and modern RAG techniques. He will also provide a brief introduction to the transformer models that LLMs are built from. Before we dive into today's presentation, I'd like to share 3 announcements about JSM. First, this year's JSM is in Nashville and will feature several SDNS organized sessions, including invited talks, posters, and contributed sessions. These events are a fantastic opportunity to engage with cutting-edge research and to network with colleagues in defense and national security. Second, Cole will be presenting Monday, August 4th as part of the Generative AI and Foundation Models in Defense Application session. That's a session directly tied to today's discussion of SysChat. And if you are attending JSM, be sure to catch his talk and explore the full range of SDNS-led programming. And lastly, on Tuesday night, August 5th, SDNS is co-hosting a mixer with the Uncertainty Quantification Interest Group at Pinewood Social. The mixer is another great opportunity to connect with JSM presenters, SDNS and UQ colleagues for a relaxed, informal evening. And then I have details for both events are also posted on the SDNS website. And with that, I will stop sharing my screen and I will hand it over to Cole to get started.
Hi, I'm Cole Molloy. As Elise mentioned, I'm a data scientist for Johns Hopkins University Applied Physics Lab, also a PhD student at Johns Hopkins University. But for today, I'll be talking about a specific application that we are working to create called SysChat or System Chat, and then generally talk about like large language models and why, APL is interested in them. So the use cases that people are interested in using large language models at APL for are pretty incredibly varied. So there are things such as new staff training. We have a lot of new staff coming in and a lot of institutional expertise that we're losing as people retire. So people are interested in, knowledge transfer kind of use cases, allowing for more holistic analysis, bringing text data into our analyses we do whenever possible. Data fusion basically with things such as sensor data and more sort of quantitative types of data, along with things such as coding assistance, automated categorization for things such as labeling training data, and many more. So we have lots of things that we're interested in using large language models for, but the issue is that those sort of tasks are not always grounded in things such as our documentation, which is important to us because we don't want it to hallucinate and, for new staff training, tell staff things that are wrong. Or even like specific to APL if they want to know about like benefits and stuff. So you can see like the example that I'll be working through is about me asking if the APL vision insurance plan covers contact lenses. I just recently broke my glasses, so that's something I'm interested in. But maybe I don't want to read the 350-page APL guide to my benefits. So what SysChat's really about is allowing us to get the sort of good uses out of large language models while still forcing it to be grounded in traceable information as we use it. Um, so first I wanted to go through kind of like why should we use large language models generally? And basically the biggest reason is they have increasingly shown an ability to do tasks they are not explicitly trained for. And they perform very well on tasks related to natural language understanding, basic reasoning, and things like information retrieval. Um, I think one of the most interesting ways to look at the history of large language models is by looking at, just the titles and general sort of feelings of the GPT papers chronologically. So the first one released in 2018, so a year after the Transformer paper was released, we have Improving Language Understanding by Generative Pre-training. So that's what GPT is, generative pre-training. Um, and at this time, language modeling was really focused in more sort of linguistic areas. So linguists were curious in how they could model language, and especially tasks such as translation. People were interested in doing that. So it was very linguistically focused from an academic standpoint. 2019, we have language models are unsupervised multitask learners, which is basically, okay, they're unsupervised now. If we give language models lots of data, interesting things start happening. So it starts creating sentences that seem more realistic, that, a human could hypothetically think that another human had written. Um, GPT-2 certainly had its issues. It's not like extremely human believable text yet. And still, for it to do any sort of useful things such as summarization or translation, you have to fine tune it, basically train it again yourself for a specific task. In 2020, we have the GPT-3 paper. Language models are few-shot learners. So moving from fine tuning to this idea of like, okay, if you just give it like a few examples of the task you want to do, it's pretty good. The text generated is difficult for humans to distinguish. And the other big thing is bigger is better. So this was one of the papers where everyone started going, okay, this language modeling is not about uh, being clever in the architecture as much as it is about more data, larger models, um, and basically the more data we give it and the larger we can do, the better the results are. Um, so between 2020 and 2023, we have GPT 3.5, which eventually gets deployed as ChatGPT, um, and just blows up and has an incredible number of users, more than I think even the researchers at OpenAI thought it would have. Um, and we see that there is a stark difference between the ones sort of in 2018 through 2020, which are very academically focused, um, but increasingly vague in sort of the implementation details, to GPT-4 technical report. It has no need for catchy titles, but it was still one of the most sort of anticipated papers because ChatGPT was at the height of its popularity, and they had been hyping up, okay, what's next after ChatGPT? What's their next big model? And we see impressive results on tasks even difficult for humans. GPT-4 technical report has very little information on stuff such as architecture and training data, what it's trained on. It really focuses heavily on human benchmarks. So things such as like, if I gave this the SAT, how would it do it? So we really see a movement away from the academic, but also this idea that scale is king. The bigger you have, the better it can do. And also just incredibly capable generalists. So if you ask it questions that you might find answers to in things like Wikipedia of like, what's the capital of Maryland or stuff like that. It's very good at tasks like that. That being said, it will still hallucinate occasionally. So there's this really cool paper called Generative Agents, Interactive Simulacra of Human Behavior, where basically they took a bunch of LLMs or a single LLM, but different agents implemented using that LLM, and gave them different biographies. So like, oh, you're a student studying archaeology at the local college, and these are the things you like and the things you dislike. And then basically put them in a sim-like environment and had them interact with each other, do things like organize events, live their lives, take actions of like, I want to go to a restaurant. So there's a little restaurant in the town that they could go to. But one of the more interesting things from that paper is that about 1% of the time, the agents would just make up facts. So it would be like, oh yeah, on Tuesday I talked with Molly about this. When that, you had every single interaction they had with each other, sort of documented, and they would just be making stuff up about 1% of the time. Um, so there is a concern with hallucinations where basically the language model is just making stuff up. And the issue is it's very hard to tell when it is making things up. So that really is one of the key motivations of like, okay, why do we need to do more than just use large language models as is? Specifically, why does APL care about large language models for information retrieval? And hopefully some of this might resonate with some of you at your organizations. Um, we have a lot of data, but it's not centralized. Um, so knowledge is spread across subject matter experts who will, by necessity, specialize into knowing specific subsystems or procedures. A lot of the analysis we do is on physical systems that are extremely complicated and have lots of subparts. And you can imagine that someone who's perhaps like an electrical engineer will know a lot about the documents that talk about like circuit boards and their connections to like power supplies and stuff like that. But they won't really know about the documents that contain technical information about maybe the procedures around repairing a part or something like that. Um, so it's extremely niche knowledge that we have. Um, and basically, if you're working on a system, let's say I need to do a design of experiments on one of them, it is very common to be just sent like these 300-page documents that are like, oh yeah, the answer you have is somewhere in here. Um, and sometimes it's just completely intractable to go out and try to read all of that yourself or find the answer to it. So it's really inefficient, and there's also information lost there, where there are probably documents that have useful information that just aren't being found because you don't ask the right person. The other sort of unique thing about information at APL is our average document length is extremely long. So usually when you look at like information retrieval type tasks, they're looking at like news articles or Wikipedia. Uh, our documents are on average 275 pages. So these are like textbooks worth of information. And a lot of that information is in things such as tables, um, which are just inherently different than just giving a large language model a news article and saying like, summarize this for me. Um, the scale of documents is really different. And what we want to do is we want to use large language models to build a knowledge base that can be queried and point users to relevant documentation quickly. And then also we want to then incorporate that user feedback and their preferences to build out authoritative sources of truth. There are documents that contain similar information, but it conflicts with each other. And right now, the process for resolving those conflicts is you go to a senior staff member and you say, hey, which of these should I look at? Um, and that's great, except people retire, and that information is lost. And we view creating this knowledge base and getting user preferences on it to be one way to help with knowledge transfer and learning which documents are really the most important to us. The other super key thing is that large language models and their associated tools are often locked behind cloud-based APIs. So it's not suitable for use with our specific documents because they are often proprietary or provided to us with clauses limiting their release. So we can't just stick our documents into OpenAI and have them use their sort of information retrieval type tools built in. Um, due to the sensitivity of the documents we work with. So that's really why we focused on like, okay, what does an APL built tool look like? Uh, so to provide some background on language modeling as a whole, a language model is an umbrella term to define any class of statistical model that attempts to make a prediction given a sequence of words. Part of the reason I want to give this background is because it's very easy um, to forget that language models are at their base statistical in nature. Um, and a lot of it it feels very like more like you're talking to someone or like this sort of intuitive process of like, oh, it understands what I'm saying. Um, no, what it's effectively doing is given a sequence of words. So the example I have is the cat in the blank. A language model will give a probability distribution of the most likely word sequences to fill the predict tag. So basically, what's the probability of uh, word at predict token position given, the word immediately before it is the word immediately before that is in, um, and so on. So you're just predicting the distribution of the next word in a sequence, um, given uh, words around it. So the most common example of this is autoregressive language modeling. So it's also called generative language modeling or left to right language modeling. This is sort of the way that we in English generate text. If you're writing a paragraph or something, uh, you don't, well, maybe you start from the end, but generally when you write a sentence, at least in it, you're going from left to right. You're starting with the words and you're writing them as we speak, one word at a time, basically. This isn't necessarily the only type of language modeling. There's other types such as masked language modeling or closed language modeling, as it's sometimes called, uh, where instead you would be looking at the blank in the hat. Uh, might be what you're looking at. And there you build out a probability distribution. And in that case, what it might look like is, cat has an extremely high probability because, Dr. Seuss is quoted all the time. So the cat in the hat is a very common phrase in English. Whereas something like, the American Statistical Association in the hat would be a word sequence with a very, very low probability because it just doesn't show up in English at all. Um, you can also perform specific tasks such as part of speech tagging or sentiment analysis. So in that case, you are, predicting this is a verb, this is a noun, and basically building out a sequence of grammar, like grammar tags or even sentiment tags. So like this sequence of words is a happy sentence, this sequence of words is a sad sentence. So there's lots sort of tasks that are encompassed in the term language modeling. But nowadays, when people talk about large language models, they're mostly talking about the autoregressive generative models. Um, Sort of to give a history of it, we started with n-grams. So n-grams is the very simple of like predict words based on word counts of the n words preceding them, uh, and then use smoothing models to model unseen words. So this is sort of the very naive, uh, you can just treat everything as like rolling a die, and as long as you can see the three words in front of it, you can predict what the fourth word's going to be. Um, this works okay. It generates realistic-ish text sometimes, especially at higher n-gram counts, such as like 4 and 5. Um, but it has a lot of issues. You're losing a lot of context because one, when we speak, we could be referencing things paragraphs ahead. So there's that. You're also losing context of like what specific words mean, in the sense that like we have things such as like synonyms, where two words could mean the same things, and ideally you would want that to be reflected somehow in your statistical model of language, because realistically, like okay, if words can be used interchangeably, um, then you want your examples of them to also inform each other. So that's sort of the motivation behind sort of the next key innovation in language modeling, which is word to vec. And this is a key intuition that two words are similar if they are found in similar contexts. And this is the start of word embeddings, which are basically like, okay, can we create a vector representation of a word from the words around it, and sort of use that to build a semantic space where similar words are ideally close to each other as vectors. And this is still very commonly used today to build out semantic spaces and then do things such as, clustering. So like if you want to cluster words together and find out like which words are related to each other, you can do that. Um, but early on, it was also used for language modeling. So it's sort of a fancy n-gram where you're capturing some of that information of like, okay, similar words are used in similar places. So then when I predict what word should come next, I can use, either one and I'm fine. Uh, Next, we have recurrent neural networks and then improvements to those, such as the long short-term memory unit neural network, LSTM. Um, where the idea is we're doing sequence to sequence modeling now. And if you have a sequence and you want to encode it into numbers and then get an output that is also a sequence, sort of the natural way to do that is through recurrent neural networks. So the idea is you create these large stacks of neural networks where each word kind of has its own, and then there might be a depth to them where you're passing hidden weights deeper on before you do predictions, and then you're passing weights, hidden weights also left and right, depending on your task. But the idea being, we are defining how information flows through the network from one word to another, and then from the input words to the output words. And basically, the issue is because we're defining those architectures, uh, we're basically providing an extreme bias towards close together words. Uh, because we're, maybe let's say we're doing autoregressive and hidden weights from one word are being passed left to right to the next word in the sequence when it does its sort of neural network step. Um, this creates an extreme sort of local effect where the information being passed loses a lot of the context from words before it. So this motivated the long short-term memory unit as well as the gated recurrent unit, where the idea is at every single step, uh, the word is deciding what information to propagate forward. So you have an actual unit, basically a vector representation that gets passed from one neural network to another, used as an input in addition to the word that's input in the next uh, like block of the neural network. Um, and the long short term allows you to basically say, this is the information you should remember, this is the information you should forget, and let's pass it along that way. Um, and this works pretty well. Like up until 2017, even into later times, and even somewhat today, you can have a lot of success using recurrent neural networks and long short-term memory units and gated recurrent units. Um, that you can have a lot of success with them, and they're pretty good at doing sequences. But the big model that most of the big language models today are built around is the transformer. And it really led to an explosion of capabilities of language modeling. Um, and the reason is it has so much more flexibility to learn intermediate features. And you're really putting a lot of basically trust in your optimization methods and saying, okay, as long as I give you the mechanisms you can learn features through, uh, I trust you to, use gradient backpropagation to learn those features. Um, so to speak a little bit more on the transformer, it was proposed in a paper entitled "Attention is All You Need," um, and attention is by far the most important mechanism within the transformer. Basically, instead of using architectural tricks to determine how information is passed through a sequence, such as a gate, we use self-attention to learn where in a sentence you should be paying attention to, depending on where you are. So the most easy way of describing this is like if you're a pronoun, like let's say it, the cat in its house, the cat in its hat. Um, it doesn't really make sense for it to be looking at in because, in doesn't have much of the important context. What it wants to look at is the noun. and the noun in this case is the cat. Um, so you basically want, when you generate, uh, the information from the cat to be more strongly propagated than the information from in. So you're basically learning how information should be propagated through the network to most efficiently give you that probability of next word given preceding words. Um, it was proposed as an encoder-decoder model. This is because it was used in translation tasks at the time. And it's extremely common for translation tasks to have an encoder that basically goes from one language. So like if you're doing French to English translation, then the input to the encoder would be your French sentence. And then you would basically just give a start of sequence token to the decoder, and then you would let it generate the English translation. Nowadays, they're used way more separately. The probably two most common examples of encoders and decoders are BERT, which is a encoder, and it converts a text sequence into a vector representation, and it will be often fine-tuned so that vector has a meaning, such as a class label. So this is very similar to like word to vec, except now instead of doing word to vec, we're doing sequence to vec. So ideally, like that encoding has some sort of information that you choose what you want it to be. So for something like sentiment analysis, uh, you would basically have a labeled data set of like texts and the sentiment that has them. And basically, you would learn to predict what the sentiment of a new piece of text is. Decoders are the generative side of the model. So when people talk about like generative models, they're mostly talking for language, they're mostly talking about transformer decoders. And they're used to generate sequences of text. Um, and the most common example of that would be GPT, Generative Pre-trained Transformer. Um, but pretty much all of like the Llama class of models, Gemini are going to be a decoder side, so they're generating things. Um, and sort of just to talk about like the most important part. So there's lots of different parts of the transformer, such as the positional encoder, which basically tells you where you are in a sentence, as well as different feed-forward layers that are just simple neural networks. In addition to a lot of this block diagram is also just like how do you combine the information that the different parts of it have together. Um, but basically, the backbone of the transformer is the attention mechanism. So I wanted to talk a little bit about self-attention and how it works. So basically, we want to allow the model to learn where it should pull information from. So what we're going to do is we're going to learn matrices of values referred to as queries, keys, and values. Uh, Basically, we have neural networks that predict those matrices, and we learn how to create them such that we maximize the probability of a correct word given its surrounding words. Um, Intuitively, how they work is queries are what are we looking for? So in this example, you can see we're basically trying to predict Z1, so what information should be transmitted from the layer that is looking at the word thinking. So the query is what are we looking for? And this is then dotted to the keys, which tell you, okay, for every single word in the sequence that you want to look at, uh, are the information you contain a good fit for the query? So queries are what are we looking for, and keys are uh, does looking at this part of the network give me the information I want? So you can see here, we basically just dot product them together. Um, when you're actually doing it, you just do that as a matrix multiplication for all your layers at once. So you can see in the formula that's represented as QK transpose. But you can see you dot them together. You normalize them by the dimensionality of K. This has just been shown to give a little bit better results. And then you run a softmax over them. So in this example, when we generate the information that's transmitted by the thinking layer of the transformer, uh, it is looking sort of 88% at the information propagated by thinking and 12% at the information propagated by machines. Um, so what information should actually be propagated though? That's what the values are. The values are saying like, okay, if you're going to look at me, here's what I want you to tell the rest of the network. So you can see here it's sort of done as a opacity. So the sort of translucent is showing like it's looking a little bit about the values associated with machines, and it's looking a lot at the values associated with thinking. And then you sum them together, and that is your score that then gets propagated throughout the network, um, and is used to actually make your log predictions of like, uh, which this word is 70% likely to be your next word. The important things are this is an example of a non-autoregressive thing because we're at thinking and we're looking at a word after it. So this might be used for like a categorization kind of task. In autoregressive transformers, tokens can only attend to preceding tokens. So you can't look ahead because one, maybe it's not generated yet. And two, if you're doing like the training step and you do have the right examples of what's ahead, um, you don't want to cheat in a way that would make it poor at generating in general. Um, and then computation time scales quadratically with sequence length, um, which is the big issue and why we need to be more clever in information retrieval than just stick everything into a transformer and have it, have it choose what information it should be looking at for a given document. That works for short documents, but as the context length gets longer, even if the model is technically capable of, having a 100-page context length, um, it's going to be really hampered by the number of heads it has. So attention mechanisms, you actually do this one time for each head. So usually a value is like 8. So you can think about that as like at any point in the network for a single word, it's looking at 8 different combinations of words. It's doing 8 different self-attention steps that are all, passing information through the network in some way. And this is also really where the crazy numbers of like parameters and stuff gets exacerbated because the larger your query key and value matrices are, the more information they can store. And to model something such as language, uh, you want them to be extremely rich with information. Um, so that's kind of why we have models that are as big as they are now. Um, that's sort of the first half. Now I'm going to talk about the applications, but I did want to give a chance if anyone has any questions beforehand. You can either put them in the chat or unmute and ask. Um,
Yeah, I don't see any questions in the chat at the moment.
okay. Yeah, we can keep going, and then if people have questions at the end too, there'll be some time.
Sure.
Um, so that's sort of the mathematical backbone of large language models. So what is retrieval augmented generation? Well, retrieval augmented generation basically is a way of using documents to provide facts and then using large language models to put them together. So basically, we're using things such as searching mechanisms to actually choose the documents that we should be looking at, and then using the natural language understanding capabilities of large language models to pull the important facts out of them. So we do this to minimize hallucinations. So large language models are really good at parroting back stuff that's in their context. So if we put correct information in their context, it will echo it back. It also allows us to trace answers back to their source. Um, so when it's creating its answers, we can also say like, oh, this was pulled from page 137 of this manual. And then the other use case is because we're automatically pulling documents, uh, you don't have the same bottleneck of like, okay, what documents does the subject matter expert know exist about this topic? So it may pull relevant documents that you didn't know existed, especially if you're someone like me who has more of a background in statistics, um, and not as much a knowledge of like the system or like system engineering kind of things. Um, it can pull information that like I wouldn't have even thought of that existed. Um, and then just general timing. So for about 15,000 pages, it takes 30 minutes to ingest all documents, and you only need to ingest them once. And we use an on-premises APL large language model, but it's the same. The large language model doesn't really matter in this case. We are using it um, pretty much as a black box where we just want it to generate things for us. And you can see this is what it actually looks like, is it's a whole process of going from a user question to an answer with intermediate reasoning steps, as well as a actual retrieval step where you're pulling the documents. So to talk a little bit about the retrieval step, so we need a way to store lots of documents and find them very quickly. So what we do is we turn text files in the form of PDFs, Word documents, and PowerPoints into strings, and then you split them into multiple subdocuments. You can imagine it wouldn't be super helpful if the tool just said, hey, it's somewhere in this 350-page long manual. That just wouldn't be helpful information. And if you tried to put all of that in the context of a large language model, it would also really, really struggle. So you split them into subdocuments that are about a page in length, but you can be smart about how you split them, on chapters, headers, whatever. And then you use an embedding model to encode documents into numerical vector representation. So that's like the BERT kind of side of it, where you're creating a vector representation of a piece of text. And then there's sort of two ways that I'll talk about a little bit more. You can either use a sort of similarity metric, so most commonly cosine similarity, um, to find reference documents that are most closely related to the provided question, or you can use a model directly trained, such as a cross-encoder, that is directly trained to match encoded questions to an even smaller set of documents. Um, and then some just key features we have that are nice is we allow for multiple libraries and have the user select which library to pull from or multiple libraries. So the reason we have it is to separate libraries based on subsystem. But you can imagine like the larger the library is and the more diverse its information, or even if you have lots of very similar information, but there's a ton of documents that are like just slightly different from each other, that can hurt performance some. So we allow users to split it out, and that makes it a little bit easier to actually retrieve the document that's correct. And then we use LLMs and other NLP techniques to actually extract metadata. So the most sort of, in my opinion, cool way or cool application of this is, or example of this is we disambiguate documents based on extracted metadata such as date. So we have a lot of documents that are just different versions of each other. So we'll use a large language, and they aren't marked with any metadata. So we'll use sort of text extraction techniques, such as large language models in some cases, to actually extract a date uh, and get the most up-to-date versions of different things. And here you can see like this sort of example of a document. It might just be a short thing, and then we get metadata about it, such as the page, the document's file path, the title of the actual document, and the date we expect it was published. So the sort of interesting mathy part of that is the cross-encoder reranking portion, and this is something that we are looking to refine even. So there's sort of two ways to do it. There's bi-encoders that turn each sentence into a vector, and then you use cosine similarity to get similar sentences. It is extremely inexpensive to compute, and basically you can create your embedding of every document as you read the documents in. So that's the plus side is you can put the entire computation of that on the front end when people are reading documents in, and then when you come to actually answer questions, it is extremely fast. Cross-encoders use BERT or another encoder-only transformer model trained to directly compute a similarity score between a query and documents. And this is expensive to compute because basically you need to rerun BERT for each document combined with the query, because the query changes every time, so you need to rerun BERT on it. So what we actually use is a hybrid approach. So it kind of does the best of both worlds. So first you use the bi-encoder to down select to a reasonable number of documents. So let's say we have 10,000 documents in our vector store. Let's just get to the top 50 of them. now it's suddenly reasonable to run our cross-encoder on 50 documents instead of on 10,000 documents. So we use the cross-encoder to more directly rank options and score them. Uh, so in that way, we kind of get the best of both worlds. And then, yeah, and so the question then becomes, okay, once you have a document in, what do you actually do with it? Um, so we do something that sort of is meant to mimic a reasoning chain. And basically, the idea is we decompose the task into subproblems for the large language model to solve, where certain RAG applications will just be like question colon, the user's question, document colon, the documents, like every single document you pulled, answer colon, and then ask it to complete that. Um, but it really struggles, especially with more complicated questions, um, because it's just very hard for it to do complicated multi-step kind of reasoning without explicitly building out a reasoning chain. So if you're familiar with like the reasoning models at all, this is sort of the same intuition as those. They've just been trained to do this. Um, so first we augment a user question using previous context from the conversation. Um, this is motivated because humans write very terse questions usually when they ask, and it's useful to add in extra information and also disambiguate things such as pronouns by giving it history. Um, and it's useful to do that before retrieval so that the disambiguation and stuff are actually part of, the retrieval process. So we do that first, and then for every document, we say read a single document and extract the facts that are related to the supplied question, scoring them 0 to 10 based on relevancy. So we aren't trying to answer the question yet. We're just trying to get facts that are relevant to the question. And then we say, okay, finally, take the given facts and scores and then use them to answer the question. Um, and this is really inspired by clever prompting techniques that have been shown to ensure quality generation. One of the big ones being chain of thought. And what the chain of thought paper says is basically, okay, if you tell a large language model to take a deep breath and think step by step before you give an answer, even in like a non-information retrieval setting where it's just like, what's the capital of so and so, take a deep breath and think step by step. It's shown to improve performance. And there's, speculation on why this is. Maybe it gives attention heads more things to look at, and therefore like biases the answer more and more towards the correct answer. So that's one thing we do. The other thing we do is we tell it it's an expert document reader. And this one's just kind of funny because at first, before we did that, it has clearly been somewhat trained at least to say, uh, you should really ask an expert about this. I'm not a systems engineer. I don't know what this system is. You should ask someone who knows. So instead, we call it an expert, and then it's more likely to be like, well, based on my guess, this is the answer. Um, and you can see kind of how it decomposes here, where I ask, are contact lenses covered under the APL vision insurance plan? And it found like, on page 99 from this specific document, the APL vision benefit option is offered through MetLife Vision. The plan covers routine vision exams as well as eyeglasses and contact lenses. And then you can see in the second document, um, it mentions, a $60 copay. Uh, and you can see both of those have a relatively high score, whereas the bottom document does not mention anything helpful, so it gives it a very low score. I found that scores are sort of relative, but it gets kind of close. So like there's not usually a big difference between a 10 out of 10 and a 9 out of 10 and an 8 out of 10 even. Um, but usually it will kind of cluster its answers into like 10s out of 10s and like 1 out of 10s and 2 out of 10s that just don't answer the question at all. And then this just sort of works generally. You can modify the chain of reasoning based on the subproblem. So if you're looking at like procedural documents, you would want to maybe decompose the problem into step by step, like looking at the procedure sort of in the order it's performed or something like that. Um, so here you can see the final answer it does. So this is what like a user would see if they don't have the option checked to see all the intermediate steps and all the sources it provides. Um, But you can see based on the provided facts and scores, I can conclude that the APL vision insurance plan does cover contact lenses, which is true. And it mentions the copay and how much of it covers. Um, so it's nice. But this is just one example. So how do we know that it's actually getting better and like actually performing up to standards? Um, so currently we have two main tests that we're working on. The first one is Squad 2.0. So this is Stanford question answering data set 2. It's a basically just a newer version of Squad, which is Stanford question and answering data set 1. The biggest difference between the two is pretty small, which is Squad 2.0 released unanswerable questions. Um, so Squad 1.0 was all about Wikipedia. Like if you get Wikipedia articles, can you answer questions that can only like use the Wikipedia articles to get the right answer? Um, so this is a question of like, okay, if I ask about the capital of a specific country, does it pull the right Wikipedia article and then get the answer right? And state of the art is an F1 score of about 92 on this task, and we get an F1 score of 90. So we're near state of the art, not necessarily state of the art, but a lot of the state of the art options are doing things such as having more language model steps where, you know, you continuously have a judge of like, okay, read the answer it gives. Does this answer the question? Are you confident? If you aren't confident, then go back and retrieve even more documents and then become more confident. So there's a lot of stuff like that you can do where you add complexity and get a higher score. But for an applied application such as ours, it wouldn't necessarily make sense. And that's also general knowledge. So the question is, okay, how can we know that it's giving good answers for the specific stuff that we're interested in? So we're currently working on implementing Ragus, which basically says sample random sections from your library of documents, so your custom one, and then use a large language model to generate possible questions that the section could answer. So basically, like we can very quickly create a generation data set or a testing data set that is specific to our documents. We also have some planned text testing. So this is going to be the subject matter of the JSM talk. So if you are going to JSM, I encourage you, if you're interested in this, to look at this because this is what that talk is going to be focused on, which is, okay, how can we then evaluate it even further and use those evaluations to make the model better? So doing things such as a large-scale user testing for qualitative feedback, seeing what people say about it, refining Ragus generated questions using SME input. So basically, Ragus creates LLM questions of varying quality. Some of the questions are very good. Some of the questions are like, no human would care about this. But we think Ragus combined with like a subject matter expert could very quickly create a very large training set or evaluation set for this tool. And then arena testing, so allowing for direct model-to-model comparisons as well as comparisons of documents against each other. And then what can we do with this feedback? Well, we can use feedback to do things such as reweight document importance from the cross-encoder and build out authoritative sources of truth. So basically making the retrieval step even better because it's very hard to actually change the large language model, but we can sort of build around it and give it the best chance to succeed it can. And then there are also evaluation data set usages to refine prompts using methods such as DSPy, which is a cool way of using evolutionary methods to basically say, okay, I have a test data set that I know is good. What is the best possible prompt I can create to retrieve information from this data set? And basically it does a sort of hill climbing way where it constantly changes prompts and sees how different changes to the prompts make the performance better. So that's another key part of evaluation is if you have a good evaluation set that you can trust, you can then optimize your sort of tool over that. Um, I would be remiss if I didn't talk about software details in a large language model talk. Because they are very large and people like to use them interactively. So software practices become very important. Here I have a table of the Llama class of models. And you can see for all of the 70B models, given different levels of precision for their parameters, um, you need at least 38 gigabytes of GPU RAM, which is extremely expensive. And if you want, like, that's a pretty much a supercomputer. Like, you would need an RTX a 6000. Um, and if, let's say, we wanted to run inference on something like Metalllama 370B at float 32 precision, we would need 311 gigabytes of GPU RAM, which is four A100s, which is effectively like you're starting to be like literally a supercomputer, but more of like almost data center levels. Um, so it's really prohibitive on what you can do. And this is also why we focus on using them as a black box rather than, you could hypothetically try to train the models, but you would need a really big computer to do it and likely a lot of time too. So we focus on using Llama 3.170B, using Opal, which is an APL-hosted large language model. So we do have a supercomputer. It runs large language models, so we use that. But it follows the exact same schema as OpenAI's API. So hypothetically, if we move to documents that were free to use with cloud-based solutions, it would integrate very nicely. Um, and then I'll just mention we offer two front-end options, which import SysChat as a Python package. So that's sort of how it's actually doing it. One is Dash, which is a Python package for creating dashboards very quickly locally. And then we also have Open Web UI, which is a Node.js application built specifically for LLM chats. Um, Sort of to move into conclusions, my key takeaways from using black box LLMs, good evaluation is key. So it's really easy to find old benchmarks that a modern LLM could perform very well on, especially in sort of information retrieval, because they've been trained on the whole internet. Um, so it's really good to like try and find an up-to-date like hard benchmark, because even though you can get very good numbers on benchmarks, they don't mean much if you're looking at an old one because the LLM has probably already been trained to be good at that benchmark. Like um, there is some criticism of them in that like you sort of game your your large language model to be good at the benchmarks. So are they in somehow like overtrained on them, overfitted to them? Um, so also like the more niche your task, the more valuable spending time to create a testing benchmark is, because like they are somewhat unsupervised learners in that you can give them a task and they might do okay on it. But it's very hard to tell like actually how good it's doing at things without creating a good benchmark. And then biggest of all, trust is important to build when deploying large language models, especially in real world operations with higher stakes than personal or academic projects. Um, so if someone writes a paper about like an LLM method, they don't need to worry about like what happens if things go wrong, or what happens if it lies more often, or what happens if it's just more convincing at lying or something like that. Um, that's very important to us. So building trust, one of the ways you do that is good evaluation. Scoping is also extremely important when pre-trained models are everywhere. Um, I don't foresee myself anytime in the near future needing to train my own language model. Even fine-tuning on modern models is extremely computationally expensive and can lead to catastrophic forgetting. It's very tempting to try and fine-tune these things because that's how, we basically did it between 2018 and like 2021, 2022, back when models were like small enough that you could fit them on a single GPU. Um, but the modern big models can be very sensitive to any sort of further training. Like it forgets a lot of the information that is good about the pre-trained, that it's been trained on the whole internet and it has ideas of like what grammar looks like and stuff like that. So there definitely are methods that make it less likely to catastrophically forget. Um, but you can get very far just treating them as a black box or focusing just on like logits, like the output probability distributions, and like, okay, can I put something simple on top of that rather than trying to train the whole model? Um, so yeah, so I think like one of the biggest areas of improvement for them is focused technical statistical work on parts such as the retrieval. I think the retrieval, like if you get the right documents every time, I think the RAG would pretty much get you the right answer every time. But it's hard to get the right documents. Prompt optimization and user testing where models are smaller and performance gains are larger. Again, just like lots of things where like why do people use the prompts they do? Well, nowadays it's a lot of times because like I guessed and checked and it turned out good. So I think there's a lot of areas where that can be improved. Um, and then my last tip is like to try out lots of things because just if you try a task and it doesn't work, um, don't assume like, oh, this isn't a task that LLMs can do. This is impossible. Because LLMs are finicky and performance can be highly prompt dependent. Um, and then sort of the conclusions of the talk. So SysChat is an application to focus performance on large-scale libraries, and we use problem decomposition and smart document management to deal with the large-scale libraries. It's flexible enough to work with other applications by enforcing strict separation of front-end and back-end development, allowing for fast integration with existing software. LLM software moves extremely quickly, so it's important, like, if you spend a lot of time generating a user interface for like a beautiful front-end tool, like that's great, but you have to make sure it works with like the newest class of large language models or whatever. We also prioritize evaluation and human feedback. This is to allow for resiliency and traceability of performance as prompts and models change, and importantly, controlled by APL. So we're avoiding using proprietary software that could require licensing or has concerns about like, can we use our data with it? Um, and yeah, through this tool, we're able to get state-of-the-art quality question answering results in as low as in 30 seconds on average. So it's pretty quick too. Um, so yeah, so that's my talk. And then yeah, if we have any questions.
I do have a question, if I may.
Yeah.
Um, what would happen if you gave the 350-page HR benefits handbook to the system and asked it to identify all the discrepancies in the manual?
You mean like without a RAG kind of, like without the intermediate like document splitting? So the short answer is it wouldn't work due to hardware constraints right now. Um, lots of models will talk about like, oh, our maximum sequence length is hundreds of thousands of tokens. But you need a computer that can actually handle that many tokens at once. Um, so I think our limits are about like 25,000 tokens, which is about 35 pages of text. So there's a hard hardware constraint on us putting a full document in. Um, and yeah, I think tasks like that where it's like, okay, do something that requires you to read a full document is definitely an interesting like domain that people are interested in. Um, RAG would somewhat struggle with it because it like something like that you need to read the whole thing because you're doing it sort of piecewise. Um, so uh, I guess the answer is like, yeah, you could try to do some sort of windowing thing, or even like if you're only interested in certain parts of it, then something like this could work out well, where you do have a retrieval, and maybe it's not like semantic similarity, but maybe you have some sort of other definition of like how to know which things to retrieve when.
Thank you.
Yeah, I see there's one in the chat maybe too.
Yes, there is one chat. Tim Trudell asks, did you try smaller LLM models to compare cost versus performance? I'm curious if a smaller one GPU model could still be useful with, say, a smaller set of documents.
Yeah, so we did try it out some. Um, so we tried out we tried out Mixtral, like a mixture of experts model that's a 32 billion parameter model. And then we also tried out the Llama 7B, so a 7 billion parameter model, which can reasonably like run inference on, but like you would still need a GPU. But now we're talking more in the scale of like something a laptop, like a high-powered kind of laptop could reasonably have. Um, and we did try that. We didn't compare the relationship between size of model and number of documents per se. We were more looking at like, given the same set of documents, how does a smaller model compare to a larger one? Um, and basically, uh, we found that there is certainly a difference in sort of linguistic understanding. It's way easier for the 70B models to like make jumps in reasoning. Um, the 7B model did okay, but it's just not as good linguistically. So it would be more likely to like do things such as grammatical errors or just say sentences that like didn't make much sense. So we ran into that a little bit, but both models were pretty good. Or I should say the 7B model was still pretty good. Um, it was just pretty obvious to us just doing like small scale like users like trying it out with like 30 prompts and stuff like that and just seeing like, okay, how's it doing generally? So we don't have like hard numbers on like, oh, we changed from this model to this model and saw a 10% performance increase, but that would be interesting and maybe something we do in the next few months.
All right, Cole, thank you for taking the time to share your research and to talk about the capabilities of SysChat using LLMs and NLP. And once again, I'd like to thank our speaker, Cole Molloy, and thank everyone for attending today's webinar. Have a good day, everyone.